Okay. All right, cool. Thank you for that. So welcome everybody. I'm Corrine Wallach. I am doing some of our developer community stuff for the Pinot community. And today we have two very interesting talks, advanced features in Pinot. One of them is about on Upsert in Apache Pinot, and the other one is JSON indexing in Pinot. So I'm going to introduce our first speaker, Yupeng Fu. He is a staff software engineer in Uber's data team, and he leads the real-time platform for scalable, reliable, and performant streaming data solutions, or streaming solutions, sorry. Stick the word data in everything. And he's also recently went from an Apache Pinot contributor to a committer. So yay, it's very exciting. So he's gonna present, and then we'll do a short Q&A, 5 minutes or so after his presentations. If you have questions while he's presenting, feel free to post them in the chat. If other people can ask them or answer them in the chat, they will. And if not, we'll save them for the Q&A at the end. And then we can go on to our next speaker, Jackie, but we'll wait for his introduction afterwards, okay? All right, so Yupeng, take it away.
All right, thanks Karen for the introduction.
Yeah.
Very happy to take the stage and share with you folks on the Upsert feature that contributed by Uber. We made this into last year, 2020, into Apache Pinot. So I can just like quickly go through this slide since Karen already did an amazing introduction. So I lead a real-time data infrastructure at Uber, and Pinot's play a big part of it. Also, we're hiring. If you have a interest or passions about Pinot and this area, please do reach out to me. First, I want to quick look at the Pinot at Uber. Pinot is a engine, I would say, the central part of our real-time platform. With our mission to provide like fast, reliable, and scalable platform to power all about the real-time intelligence across Uber. And you can see many keywords here are our internal use cases powered by Pinot. One very interesting customer-facing application built on top of Pinot, this is Uber Eats Restaurant Manager. It's provided to the restaurant owners on the Uber Eats app. So the restaurant owners can look at some key insights, information about their restaurant performance, like the sales, the popular dishes, not only for the past day or months, but also look at this in a real-time way, like in the past minute hours to see the trend, and then perform some action accordingly. Here's our overall architecture of the platform. You can see Pinot is a central storage engine and also the for the query part as well. And on the left-hand side is about like ingestion. So Pinot can ingest data from both the real-time part and the offline data, which is on the HDFS. And Pinot itself provides this inbuilt Lambda architecture so that I can stitch the real-time data and offline data nicely and present this holistic view to the end user, which is through this Presto layer that we, Presto is also pretty heavy use inside Uber for the query analytics. And we try to use the same the query flavor across the different query engines like Presto and Pinot to simplify the user experience. This actually the feature also contributed by Uber to the Presto community. Some interesting numbers to show that today at Uber, we actually have pretty high QPIs. Pinot is like 15K per second. And the data freshness is very important, and we provide like less than 30 seconds freshness and pretty low query latency. For majority of queries, it's like less than 100 milliseconds. And we built this internal self-onboarding platform around Uber, which is another our Uber internal orchestration layer for the self-onboarding. And the people use SQL to query data. So why we want to build this Upsert feature and contribute to Pinot? Because by nature, data can be updated or be corrected, and therefore the Upsert is a very common data operation in the source of the data. So to show a quick view of how this feature is used, you can see on the Uber Eats side, we have a live dashboard to show ongoing orders, say like in a city or in different countries. The key metrics that our operation or operator, they care about, like for example, how many ongoing orders they are live and how many completed, and what's a breakdown for the past 15 minutes or an hour. And this dashboard can be easily built on top of Pinot. You can see on the left-hand side, we just run a query to do the count on a particular region. In this case, it's San Francisco, and we group by the different status of order. But naturally, the Uber's business is really real time, right? So the status can change, can be updated from like order being placed, or there's a courier delivering this order until the order is completed. So without the correct data update, then the numbers shown here will not be correct, right? You will include the historical data without showing the up-to-date view. And that's why Upsert is so fundamental and important for us to show accurate and up-to-date real-time view. And if you're familiar with SQL, you know that there's no very easy workaround to express this Upsert semantics in SQL. That's why some fundamental changes are needed to the query engine into the Pinot. And because Upsert is so fundamental at the data layer, that there are a wide range of applications can build on top of it. It just at least a few other internal use cases. As you can see, the status of order can change, and similarly for the fares of rides can also change. And you can see there are several other Uber internal platforms also demand this real-time change of the data. So this is a pretty fundamental feature that basically all the use cases can benefit from. But Upsert is pretty challenging, and hopefully in this talk I can go over some interesting innovation that we did to make this feature successful inside Pinot. Why the Upsert is difficult? So this slide shows a Pinot real-time data flow, particularly how it's ingested from Kafka or how it's landing into the Pinot servers. I borrowed this slide from another amazing talk Chimi Soman did as the introduction to Apache Pinot. You can find the slides at the short URL at the rightmost corner. I would say there are a couple of key insights we want to get from this slide. One is that Pinot split the real-time data and group them into segments. And in this case, you can see there are like 4 segments. And these segments are distributed to different servers, both for the reliability, but also for the better performance, so that we can run a query in parallel without hitting the bottleneck of one server. And lastly, the segments are replicated, so that for each segment, there are multiple copies of it across different servers. In this case, you can see there are segment 1 to 4 split to 4 servers. And by default, there's no like inherent like rule on how these segments are distributed. And this can create like challenge for features like Upsert. Like for example, you can see here that for Upsert, like data is identified by a primary key. And essentially we want to track the information of the data records that share the same primary key, right? So in this case, you can see assume there's one record of primary key 1 in segment 1. And the next record, which is record to update this primary key 1, is in segment 2. but they are on different segments, and in this case, are on different servers. So the challenge is that how we can identify this relationship of the records across different servers, and then do coordination in an efficient and fast way, because we have a pretty strong real-time requirements on the data efficiency side. So to address this fundamental challenge that we had a very first attempt, almost like 2 years ago, that we try to build a central coordinator to establish this information that you can see in this architecture that we want to collect the information from each server, particularly on the metadata like the primary key, aggregate this through into one Kappa topic. This is like an internal topic to Pinot. And then we add another module into this Pinot cluster. We call this a global coordinator, which has this global view or global information. So that when there's some update happens, the global coordinator has this knowledge and then can dispatch some instructives to the different servers. And in our particular design, we do this in the annotation way by adding virtual columns to each server, so that each server know which piece of information is updated and then do this coordination. We explored this approach for about like 1 year plus of both dev and testing, but we hit some challenges getting this into production. Though this approach has some advantages that basically we're building like surrounding components around Pinot core to add this Upsert awareness. But there are a couple of like system level disadvantages. One is that this additional component, this global coordinator, is become a single point failure. So we have to add the fault tolerance property to it, which itself is pretty challenging as people who are familiar with building distributed systems. Another issue is around the Kappa topics, which serve as the data collection and dispatching. And you can see the number of messages in this Kappa topic is proportional to the overall data you ingested from Pinot. And this is not only for one table, it's for basically all the tables across cluster. And this become a scalability bottleneck because of this central coordination and information collection. There are other challenges like adding this query writing complexity and therefore become like a blocker to adding a partial update, which is another feature we want to support on our roadmap. So we look at this overall architecture, and then we made decision that we felt that it's too complicated and still be far away from fully productionized. And then we made a result of the design to see, can we do something different or can we do something better? So let's take one step back and see what's the fundamental challenge we want to address in this problem. To some extent, the key challenge is to establish the global coordination problem. For people who are familiar with the distributed system, this is actually a pretty fundamental challenge to any distributed systems. For this global like state, like management or control, basically there are two ways. One, use some centralized system like Zookeeper or Route protocol to manage the state. Or alternatively, we can reduce this into a share nothing architecture, which basically to partition or shard the data into different partitions. In this case, as I show in the diagram below, you can see before we have two partitions, and each partition have a few segments, and there's no like partition rule here. Alternatively, we can group this partition by splitting them into different partitions. And we store this partition on each partition on each server. So this basically takes the direction of going after the share nothing architecture. So we call this approach a local coordinator, that we use a stream processing engine, and in our case, it's a Flink, to repartition the input Kafka by different partition keys. And then we make several changes to the Pinot core, Pinot architecture. One is to add this local coordinator to track the primary key to the record location mapping. So that you can see this is no longer a global coordination problem, but reduced to a local one, that each server only needs to know which records need to be updated locally without talking to any other machines. And we add another index, which is a bitmap, to track all the documents that are being skipped or to be updated. So this information is useful for the query time, that we can safely skip the documents that are no longer like the latest state. And next, we need to change the stream ingestion part to correctly update the metadata per record, as you can see here. And as mentioned, that the query executor should also be aware of this information and then use it to process query correctly. Lastly, the broker needs to dispatch a query to the servers. But here, there's additional requirements to the query that need to dispatch all the segments of partition to one server for processing. This is for the consistency requirement, that each server has a full knowledge of a partition. So let's look at again about this approach. The advantages is that we significantly simplified our architecture. No modules, no new roles like global coordinator is needed. Everything is built into the Pinot core. And because there's no additional components added, we also solve this skippability problem because of this share nothing architecture. The challenges is one is that we have to make a major surgery to Pinot core. And luckily, we have a pretty good support from the open source community, and collectively, we made this feature into the open source project. The other challenge is that the additional requirement that the input stream must be partitioned correctly using some stream processing engine. And as mentioned in the very beginning of this talk, inside Uber, we have this self-serving platform, and we try to make this step as simple as possible by leveraging some existing work that we did on the Flink side. Like Flink supports Flink acquired language called Flink CQ. And we try to make this like a simple configuration change by annotating the Flink CQ to say, hey, the query should be partitioned by some given columns in the query. And therefore, we can make this partitioning problem to be very simple, just like a single line of a configuration change to our internal users. So I try to give some quick example to see how the data flow goes into the Upsert table. This gives you like one quick example of some segments on one local server. You can see this table name, let's call like Uber Eats. And currently has two segments, segment 1 and 2. The first segment is already sealed. And so the second segment is ingestion and buffering the memory. There are some already records in the table, some orders like ABC with their states like one is already created, and the other two are already assigned to some drivers. And another order called E that's being picked up. Now you can see for the key data structure is that we need to build the index from the primary key to the record location. And the location, basically the information includes the segment name, the document ID of this record, and also timestamps. These are the minimum set of information we need to track to support or be aware of Upsert. Next, there's an update of order B coming in, saying that this order already being picked up with a new timestamp T6. So the way we update the data structure here, one is that you can see we need to cross out the existing mapping from B to the old record location. And we add a new mapping, which points to the new location of segment 2. This is pretty straightforward. And next, so let's see, there's an update on the record of the mutable segment, which is E here, that changed from pickup to delivered. And you can see comparing to the index, I use a yellow color to indicate the update, but not addition. Comparing to the previous slides, we have the E with a T5 and the doc ID 0, and update to 2 and T7. So that indicates the update for the records in the mutable segment. So this just gives you a very high level view of how the index updates as different updates coming into the from the Kafka stream into the Pinot segments. Just share some the journey thus far and the planning we had ahead of us. So the Upsert attempts actually start pretty early. Like in 2018, we already start looking at this problem. And we spent a year on the initial attempt, and then we decided to redesign it in June last year. Actually, because of the simplified architecture, we made pretty good progress on the second design. It's pretty fast that within 5 months, we finished the feature and we rolled this out in the Pinot 0.6. And then now it's running in the Uber production clusters. So if you're interested, you can take a look at the release notes and also the documentation we have on the open source Pinot docs. And there's also a design doc. If you're interested, you can take a look how we explore the feature and overcome the challenges. Show a very quick screenshot of what is the Upsert is like in action. You can see this kind of the query I showed in the beginning, where we want to group by, not group by, but we want to filter down like a production UID, and we want to show the order status. You can see for this particular order, it is the status changing from created to assigned and then to pick up completed, right? And with Upsert, this will always show the latest status. So you can see that only one record shows up. And because of the way we designed this feature, it's actually pretty nice that we could disable the Upsert on the fly. This is possible because we didn't modify the data in place. Instead, we use additional data structures to track where the latest record. And we use this information as a filtering operator in the query. That's why we are able to disable the Upsert when we want to, right? Like this can be done through a concept called like query options, where you can attach this config to say disable Upsert. Then you still see the results as a normal table with the Upsert feature. We have found this feature pretty handy when we want to do certain analysis. Like for example, we want to see how many updates per UID or per order. Instead of seeing the latest status, we want to track the historical updates. so that you don't have to create another table, a non-Upsert table one for this purpose of query. Instead, you can just use like this query option, and then you are back to the previous mode, which is like the append only mode, to see the history. For the future work, there are two broad directions we're working on. One is that with the existing work that we solved the Upsert in the real-time ingestion, so we want to look at a problem that what if a user wants to longer data retention, right? Instead of keeping data in the kappa buffer for a couple of days, users want to return data for like a year or over a year. And in Pinot, this kind of long retention data is solved by a hybrid table, this concept. And there are basically two options to explore. One is that we can extend these Upsert concepts to the hybrid table, especially the offline part. Or alternatively, we are thinking about that just to push the segments into the real-time table, so that you still have like one table, but this include different segments, both for the real-time that you ingested from the Kappa stream, or you have the offline segments that previously push into offline table, but now you push to the real-time table. The key difference here is that now with the Upsert metadata, we actually have the ability to track the relationship among different like records. So this work is actively under design discussion. If you are interested, you can take a look at this Pinot PR that our team member like already make some code change, and this is being discussed in the community. Another direction is that we want to support the partial update. This actually is a convenience to the user that instead of describing the full changes or full records in the Kappa stream, alternatively, user can only describe the payload itself and omit the other columns that not being modified. Again, the change on this part is that there could be different merge strategy to resolve conflicts. So we already have a design posted under this Pinot like issues. If you're interested, please go take a look and review the design. So that's pretty much it. Thanks a lot for you attending this talk. I'm happy to take questions from here.
Awesome. Thank you, Yupeng. That was great. Great work. This is awesome.
Thank you.
Okay, so we do have a couple questions. One of them I think was addressed, but I'll ask it. And if it was addressed, just be like, skip, okay? So Upsert also depends on the target table type. What type of target table in Pinot, type 1 or type 2? Because depends on the type of target table, the Upsert logic will be varied.
Could you clarify this like by type? You mean like what's type of 1 or type 2? Do you mean like real time or hybrid table here?
I'll give William the option, the opportunity to write his answer. We also have somebody else who asked a question, but it looks like it was addressed. And so then while William is responding to that type 1 or type 2 thing, we'll ask the next question. Why do we need to use time column to determine the latest version rather than specifically a column? We use time column for created _at and a separate column for updated _at. Would be nice to have flexibility on which column to use to determine the latest, to specify.
Yeah, that's a very good question. So when we first build this feature, we primarily only looking at the Uber internal use cases. And for Uber tables, we primarily use like one time column, which actually the same time column built into the like open source Pinot. Because Pinot is this kind of time series database, when you create the schema or the table, you need to specify a time column. And naturally, the value in this time column become an indicator that which record is the latest one. But we do see that there's some aspect like this, and there's an issue created on the open source project issue. And
yeah, Chinmay shared it.
yes, I think it's reasonable and it's not very difficult to extend, so that going forward we can add this flexibility so that user can specify it.
Cool. Somebody said thank you for the great presentation, and also asked, creating a mutable segment, are there any performance implications for sorted index columns?
I think this question, I want to make sure it's about Upsert or about non-Upsert table here. In general, you can think of for the mutable segment, it's a buffer. It's a buffer in memory so that as data flow in, Pinot is able to serve this data to give you the latest insight. So all the data structure ingested are in memory and stored as in-memory data structure. When the segments are sealed and flushed out, that Pinot will materialize this data and create on disk data structure. And these sealed documents actually can be used in more efficient way. When I talk efficiency, I'm talking about like memory, using the off-heap memory. But for the middle part, everything is in memory. For the upsert metadata here, that because there's essentially the upstream metadata is a map, right? You want to track the mapping between your primary key to your record location, and it'll be frequently modified so that this data structure is kept in memory for lookup efficiency. And we have been very careful about like how we can make this data structure as small as possible and only retaining the necessary information within this map. So there's definitely like one particular optimization that we did for this feature.
Cool. Hopefully that answers the question. I mean, it did answer the question. So thank you for answering the question. Tim said thanks. All right, cool. We can give another like 10 seconds if anybody has any other questions. Just, I don't think they have the hand raise in here today. Sometimes they have that hand raise emoji, so you can be like, I have a question. But if nobody does, then we can go on to the next presenter. Okay, okay, so yeah, nobody, this is the answer to the question.
Cool. Thanks everyone. Now I'm going to transfer the host to
Yes. And Yupeng's also going to be here to answer questions in the chat. So if you have additional questions, he'll be here also. So you didn't lose the opportunity. All right, cool. Thank you so much, Yupeng. And great job on this. This is cool.
Honor here.
So I'll give you an introduction to our next speaker, who's going to be speaking about JSON indexing in Pinot. Jackie got his bachelor's degree from Tsinghua University and a master's degree from Carnegie Mellon. And then he started his career at LinkedIn for 4 years and then became the PFC and one of the top contributors for the Apache Pinot project. Jackie's goal is to make Apache Pinot the fastest online analytics platform on the market. It's a very big goal, but I think he could do it. So it's cool. All right, so Jackie, you can take it away.
Hi, everyone. I'm Jackie. Can you see my screen?
Yes, we can see your screen.
Oh, okay. Thanks, Karen.
It's perfect. Yeah.
For like hosting this meetup. So yeah, today I'll discuss about a recent feature added to Apache Pinot, the JSON index. So yeah, so I'll first discuss like how do we store the JSON data inside Pinot, and then why do we need JSON index? Then like as a user, how do I configure the JSON index, and internally, how do we build and use JSON index? In the end, I'll like show some number of the performance comparison with and without the JSON index. So let's see how to store JSON index. I will use an example from the Meetup RSVP stream data. And then, yeah, actually, like I randomly pick a message from this RSVP stream data, the Kafka stream. And here's the example message. So, so we can, as we can see, like it's a pretty big message, and inside it contains some JSON field and some simple field. Like JSON field include like here we can see the venue, the member and event, some nested JSON field, and the visibility is the simple field, which like yeah, which doesn't have any like nested structure inside. Also, there's another very interesting field called group. So actually inside this group, there's another level of nested array inside called group topics. So, and it's a pretty big field inside, except for the group topics, there's also like group city, group country, a bunch of other fields. So that leads to the question, how do we store this data? So basically, there are multiple options. First option is, can we store it with fixed schema? Like, I mean, most Pinot use cases, we enforce a fixed schema to hold all the data. So for example, for the simple field, it's very simple. Like we just map each field to a column in the schema. But how about the JSON field? So for the venue and event, because there's a fixed schema for this JSON blob, actually we can map it into, like, basically we can flatten it. So we can store like venue name, venue longitude, latitude, ID. So we can like similarly for event, we can flatten it. So we are able to use fixed schema for them because basically they are structured data. But how about this group field? It's nested. So one option is, can we store it as multi-value column? For example, we store like, we flatten it, and then we store multi-value URL key as like AI software engineer and array, and then we store another multi-value column for the topic name. Then the question is, what if there's another level of nested objects? Let's see, like URL key is another JSON, like another object, and instead of a simple field. There's no way to represent that as a multi-value column. So this approach doesn't work, or it doesn't work for all use cases. So another approach is, let's see if I can flatten all this like array elements. So for example, I can flatten it to group topics URL key 1, 2, 3, and then also topic name 1, 2, 3. But then the problem is, what if there are like 100 group topics? Like, do I create 200 columns for that? And then in that case, what if there are like 200 group topics? It's not scalable. Then like another approach is we directly store the JSON blobs. Then like for the storing part is very straightforward. We just put the JSON string into these columns. But then the question would be, how do I search for a particular event? For example, I want to know the event with name, here, data science in investments. So because it's stored as JSON blob, we need to extract the fields from the JSON. So luckily, we have this inbuilt function in Pinot called JSON extract scalar. So it's leveraging the JSON parse library to extract any field within a JSON string. So let's look at some examples. So first example, like give me all the events at this venue ID. So what I can do is I can select the event from this table, and where we extract the venue ID from the venue field, which has value like the ID I'm interested in. So second example, like give me the name of the events with the first group topic, artificial intelligence. So similarly, like JSON extract scalar, like provides the functionality of extract a field within a specific array index. So we can do like JSON extract scalar on the group topics 0, which is the first group topic. And we can extract its name, and then we can use it to match artificial intelligence. The third one, for example, I want to know the name of the events with group topic name artificial intelligence. Like, I don't care which index it is in the array. I don't know how to do that because JSON extract scalar, you need to give it a specific index, or it doesn't know which field to extract. Then there's no way to compare. So right now we see like two approaches. Let's compare the pros and cons for these two approaches. First, for the fixed schema, the process, we already have like very rich indexing techniques inside Pinot to make the query very fast. But then it cannot, firstly, like you need to take some extra effort to extract the fields from the JSON block. But more importantly, it cannot support nested structure. So that's not like optional in my opinion. And then for the JSON blobs, it doesn't have any cons of the fixed schema. But the main problem is it's very expensive to query. So because we actually store the JSON string, for any filtering query, we need to first build a JSON object from the string, and then we extract a specific field from the JSON object, then compare that with the actual values we want to look up. So the problem there is for any filtering, you need to scan the records one by one. There's no index built on top of it. And another thing, I think it's kind of minor, but it's also like needed for a lot of use cases. Is like, as I showed before, it cannot search elements in an array without a certain index. So that leads to like this JSON index idea. Like we want to build some index on top of JSON, so we don't need to reconstruct the JSON object and then for any lookup queries. So basically, JSON index is an index applied to a JSON blob column to accelerate the key value lookup. And the idea is very similar to inverted index, but it's on top of all key value pairs within the JSON blobs. So next, I'll first talk about how to configure JSON index. It's quite simple. So in the table config, there's a table index config field. And then inside, we introduced a new JSON index columns field. And then it's an array, and you can put all the columns you want to add JSON index to. So in my example, there are 4 JSON nested fields, venue, member, event, group. And this config works on offline segment generation, real-time table ingestion, and also this config can be added on the fly. So basically, you modify your table config, you reload all your segments, then the JSON index is ready to use. It's very convenient. And then next, I will go into the internal, like how do we actually build the JSON index and how does it work? So to build the JSON index, first, we want to flatten the JSON records into all these key value pairs. Let's take the group as an example here. The flattening for the simple fields like group city, group country, like it's direct, we can directly map it to a field. But for the array fields like group topics, the flattening, I want to replicate the simple fields into all these 4 group topics. So the flattening result is shown on the right-hand side. So as we can see, like all these 4 flattened records have the same group city, group country, and group ID, but they have different group topics. The second step, we want to build inverted index on all these key value pairs. So on the left-hand side, I have the flattened records. So then I can build inverted index on top of it. Basically, the inverted index is on each key value pairs. So the value for the inverted index is actually like key equals some value. And then as we can see, like for all the group topics fields, there are only one flattened doc IDs. Yeah, there are only one flattened doc IDs. But for the simple fields, because we replicate it, so for group city, group country, and group ID, there are 4 flattened doc IDs. And then we also maintain an extra level of mapping from flattened doc IDs to original doc IDs. I will discuss why do we need this in the querying side. So there's another problem not addressed yet. If we flatten in the way I showed in the previous slides, the array index info is dropped. So how do we keep the array index? I want to know like which index has, for example, I want to know the first group ID. Then I need to keep the array index info. So here we actually introduce a new virtual column called like $index. So that's information for the array index. So on the left-hand side, I add this index, and then when I create an inverted index, I also build that into the key value pair. So as we can see on the right-hand side, group topics index equals 0 map to the flattened doc ID 0 and original doc ID 0. Okay, now we have everything. How do we use the JSON index? Let's take some examples. So for example, I want to find all the records with group topic name software engineer. We can use the mapping we already got, basically the inverted index we built previously. So we want to know all the group topic with name software engineer. We look up the key value pair with the key plus software engineer. And then we found, okay, there are 1 flattened doc IDs associated with it, the flattened doc ID 1. Then we need to look up the next level of mapping from flattened doc ID to original doc ID, because the original doc ID is the one we want to use. So here, the flattened doc ID map to the original doc ID 0. So we know, okay, in doc 0, I have a match. So basically, we found the software engineers, the lookup for, we found a match for this lookup query. So another example, let's see, I want to find the records with the first group topic name, artificial intelligence. So here, we need to use the array index info. So we need to look at 2 things. One is the topic name, artificial intelligence, and also we want to look up the index, which is 0. So here we found 2 key value pairs. So we found 2 sets of flattened doc IDs. By the way, this flattened doc IDs is stored as a bitmap. So like any bitwise operation is very cheap on top of it. So basically, I need to know, okay, so the group topic name is AI, and then also the index is 0. So I need to do an AND on these 2 doc IDs. And then I got, okay, flattened doc ID 0 matches like these 2 conditions. And then I do another lookup in the original, into the original doc ID. And then I found, okay, this doc actually matched this criteria. Another example is I want to find the records with the second group top ID, top name AI. So here we can see, like, again, I need to do two lookups. One is the topic name AI and the index 1. And then I found flattened doc ID. One has flattened doc ID 0 and one has 1. If I do an AND operation, there's no match. So I know, okay, there's nothing matched. At least like this record cannot match this criteria. That's where like the index info is really useful. And that also explains why do we need to keep the flattened doc IDs separate from original doc ID. Because we need to use flattened doc ID to solve multiple conditions and then do like an operation on top of it. Okay, so next step, I want to talk about how do we actually write the query to use the JSON index. So here we provide a new predicate called JSON match. So that's, again, look at some examples. First, if I want to know all the records at this venue ID, what I can do is I can do a JSON match on the venue field where the venue ID equals the ID I'm interested in. It's very straightforward. And also, for example, I want to know the records with group topic name AI. So this is something we cannot do with the JSON extract scalar. But with JSON match, it's very simple. Like you just say, I want to know all the group topics with topic name AI. So third one, I want to know the records with the first group topic name AI. So again, it's very similar to the JSON extract, where you can put a array index inside the search expression. Again, like it can also support nested filters. Like I want to know the records with AI as the topic and then the group city as Singapore. Then I can do, like in the filter expression, I can do like nested and filter expression. Basically, JSON match takes the JSON field column and also a filter expression. And it can achieve all these JSON extract functionalities. So next, I want to show some like performance comparison numbers. So as I said before, like the JSON extract is extremely slow. So here, the example, I created 10 million records as one single segment. And then I want to find the records with person's name added. So actually, these two queries give me the exactly same result, but the JSON extract scalar takes 11 seconds. And the JSON match is extremely fast. It only takes 10 milliseconds because basically it's an inverted index lookup. Yeah, that's pretty much it. And also we have built the JSON index into our quick start. Feel free to try it out in the quick start JSON index batch and quick start JSON index streaming. Thanks. And then, are there any questions?
Awesome. Thank you so much, Jackie. And Yupeng. Thank you guys so much for this. So I did ask if there's any questions. If there's any questions, please write them up now because it takes time to write them up. And if we don't see them, then we're just going to be like, okay, bye. But Ken did say something. He said, waiting to find out about aggregations on nested JSON fields. So can you use result of JSON match and grouping with aggregation?
Let me take a look at the question.
Okay.
I don't fully understand result. Actually, the JSON match is modeled as a predicate, so it can only be used within the filter. You can think of JSON index as another type of inverted index. It works on JSON blob columns. So it doesn't work on grouping because it's not a UDF or it's not a transform function.
Okay. And if anybody has any other questions, I mean, since there's no questions in the chat, if anybody wants to like turn their microphone on, you can ask the question verbally since we're here. And I think the group is like not enormous. Feel free to ask. Okay. So I'm going to assume that there's no more questions unless someone wants to turn on their microphone or say something in the chat. If not, then okay, cool. All right. So I think that's wraps it up. I think that's it. Thank you guys so much for doing this. I really appreciate it. And thank you guys, everybody, up for coming. And also, just for future reference, like my name's Corinne Wallach. I'm going to put it in the chat. I'm in the Pinot Slack. If there's any suggestions for like topics and things like that that you're interested in seeing in the future, please just ping me. I'll see if I can somehow find it out. But this is definitely a cool one. So thank you guys so much for sharing. And people are thanking you guys in the chat if you can't see it. And we'll post the recording this week as soon as we have it.
Thank you.
Okay.
Cool.
Thanks,
thank you
Karen,
guys
for
so
hosting.
much. No, thank you guys for preparing a presentation. I literally did nothing. You guys are the ones that did all the work, working on these things and building stuff in Pinot, and it's cool.
Cool.
It's really good stuff. It was great presentations. All right.
Thank you.
Well, thanks everyone. Have a wonderful day. Thank you for joining us, and we'll see you at the next one. Bye.
Bye. Bye.